All right, let's start. So welcome everybody to this week Autonomy Talks. This week is a pleasure to have Andrew Spielberg from MIT. Andrew is a PhD candidate at MIT CSAIL and is supervised by Professor Matusik and Rus. So Andrew holds a bachelor and master in engineering and computer science from Cornell University and previously worked at Johns Hopkins University at also Disney Research. And his work focuses on the fabrication of robots, and he creates tools to enable the design of rigid and soft robots all the way from the first concepts to the actual production of the robots. I got to see some of the work he did personally. It was very, very cool. And I'm really excited about this talk. So go ahead, Andrew.
Thank you so much. All right, super excited to be here. And so let's just dive right into it. So today I'm going to talk about some of my work and also my thoughts on where the future of robot design could be going. And so let's just get to it. And I think the best way to start about talking about what we want robots to do is sort of look to nature, right? Nature is super diverse and super capable. You have creatures that can run super fast on land, crawl, climb on walls, jump several body heights. You have creatures that can swim extremely fast, and you also have like super resilient animals that can basically take any sort of beating possible. And when we think about what we want robots to do, a lot of times we think that we want robots to aspire to the capabilities of nature. And why are organisms so much better than current robots, or why are they so impressive in general is largely due to their complexity. Organisms have several organ systems working together in order to solve whatever tasks we want they want to solve, right? So they're able to sense their environment around them with dense neural arrays and skin. They have actuation and muscles placed in strategic parts of their bodies so that they can move in ways that will afford them to be able to solve certain tasks. Encoded, obviously, just into the structure of most organisms is either an endo or an exoskeleton, and that encodes a topology or a shape of the creature. And not only is there a skeleton to these creatures, but also organisms have a gradient of rigid and soft components where there's bone, there's tissue, there's fat cells, and this gives a type of material intelligence to the structure of the organism itself. And so when we think about the human hand, for instance, we realize that built into the fact that there are soft parts on top of bone, we're able to do things like more dexterous handling of objects, and the same thing goes for the feet. We have rigid and soft parts of the feet, which help to have more stable landings. And all of this is tied together by a very capable central nervous system for most organisms, which can do planning and cognition, or at least most animals, right? And this allows them to figure out how they're going to solve tasks and also how they should control their body. This has been described as a cheap shot by some, but by comparison, the state of the art a few years ago is the DARPA Robotics Challenge, right? Obviously, we've made some strides since then, but the robots that you saw there, even though they were extremely capable, they're more capable than other robots before, they still failed in a lot of ways. And part of the reasons why they are so lacking robustness and why they're so not agile compared to the organisms that you see in nature is because of the structure of these robots, right? They're not complex. They're rigid components. There's not a lot of sensing on them. The actuators probably leave a lot to be desired. And if you look at all these robots that you see here, you're going to see a ton of different bipeds, but they're all really similar, and they're all suboptimal, I would say, right? We haven't nailed what is like the perfect biped for robots, because that's a really hard design problem. Like I said, they're going to be really complicated. But we have made a lot of strides. So on the bottom right here, this is Atlas, one of the bipedal robots from Boston Dynamics in 2010, and the version that you see in 2020, which we've seen can do parkour and backflips and all sorts of cool stuff. That's a huge progress. But I could also say on the converse side of things, it took 10 years to get from where you see in 2010 to 2020. And the robots still can't do a ton of tasks that we'd want our humanoid robots to do. And so if it's going to take 10 years to get there, I'm wondering how many more decades is it going to take for us to get to the super capable robots that we want, working in our households or working besides us. And that's just for humanoids. If you want a real diverse array of robots, we're going to need much, much faster ways to design and fabricate these robots. These current workflows, while making great strides, are not fast enough if we really want to explore what's capable. And that leads to the main thesis of this talk, that if we want capable robots, we need to make it easier to explore algorithmically, that is purely by computer design, and manually. That's where I say that a human is working side by side with the computer in order to solve tasks, in order to design the robots. And so I'd like to just ground this for a second with a quick example, right? On the, these on the left-hand side, these are robots that have been designed completely by a computer for a task. So the topology and the controller have both been co-designed together for all these robots in order to allow them to walk forward. And I'll show more examples of this later. On the other side of things, you'll see, you can also have workflows where humans work side by side in CAD-like programs where the system is helping the users to assemble robots. So it's resizing the components as necessary in order to fit constraints. And as I'll maybe show later, the system can also guide the user through interactively in order to suggest how to change different parameters in order to make them optimal for certain tasks, such as walking forward or conserving energy, or being able to turn in place very well, right? So these are two workflows that are really going to enable better, faster design of robots in the future. The world of robot design is huge. It's growing faster and faster, but the reason why it's huge is because every robot has two parts, I would say. There's the brain and there's the body of the robot. And these two work very closely together. And there is some overlap between the two, but for the sake of discussion, we'll say that the brain includes, control, sensing, proprioception, sensory motor skills, and the body is all about the structure, what the topology of the robot is, what the shape of the robot is, the materiality of the robot, and so on and so forth. And also, there's a spectrum of different types of robots that we would want to design. There's the traditional rigid robots, which I've mostly shown in the last few slides, but as we're going to see soon, there are also soft robots. And these robots are continuum bodies, and they move in very high dimensional ways. And then there's a spectrum in between, as we'll talk about at least at one point in this talk, where we have some rigidness and some softness. And this is actually a very difficult problem, but these different components are needed for different types of robots. So for some robots, you need, depending on the rigidness or the softness or the types of tasks you're trying to solve, you might need certain components to be optimized. And for other types of robots, you might need other components to be optimized, right? And so this leads to this idea of computational stacks. And this is an idea I want to talk about today to motivate the remainder of this talk. When you have a computer stack, a computer is able to take electrodynamics, convert it into analog circuits, which are then used to create digital components, which are used to create binary signals, which are then interpreted in machine code, and then you have programming languages, and then you have some application. And each layer of this stack has been modularized and abstracted away from each of the others. And this is really nice because this means that we can change different layers out in order to use whatever is best for our downstream application, right? So, if I decide I want to code something in C++ versus C# versus JavaScript, depending on the application, I might choose any one of these programming languages, but it's compatible with everything below it or above it. We have different, ARM architectures versus x86 architectures for the components, but we make sure that everything above it works in an abstracted way. And I'm hoping that this is sort of where we go with robot design. So specifically, this is my idea of a robot design stack. And today I'm going to be talking about how different projects I've worked on have fit into this robot design stack. And there's tons of great work out there, and you can place that in different layers of the stack. And I'm hoping for a future where we have capabilities that can all interplay with each other, and we can really take quick advantage of the incredible capabilities that we're coming up with. Today, I'm going to be talking about the top 5 layers of the stack, but I'd like to start at the bottom and just briefly say that the reason why computational robot design is so possible these days, and why it's really grown over, say, the last 25 years as a field, is because the hardware has gotten better. So we have parallel multi-core CPUs, and we have high memory and high core GPUs that are really allowing for fast simulation and optimization techniques, which are going to drive the higher levels of the stack. I also want to give a quick shout out that there's great programming languages now that encode differentiability and directly interface and optimize for this different hardware. I haven't worked on this, but there's some really great work here, and I think it's going to be very important to the future of robot design algorithms. But above that is where I've been focusing over the last few years, and I'd like to talk about each of these layers. So first, we're going to talk about fast, differentiable, and accurate simulation, which is going to be necessary as an inner loop of all the steps above here. So without good simulation, it's going to be very hard to do good design in a fast way. After that, we'll talk about co-optimization algorithms. How can we use simulation in the loop in order to optimize robots for different functions, for different tasks? Above that, we'll talk about learning algorithms. How can we exploit good optimization algorithms in order to learn more complex structure? And then after that, we'll talk about the front-facing side, the interactive user faces that people can interact with, and also predictive, hopefully predictive ways that we can create fabricated objects that actually match the simulation. So with that in mind, let's just jump right into it. I do want to mention really quickly, I'm going to go up the stack, but a lot of the projects I talk about today are going to involve both rigid and soft robots. So I might be switching back and forth between this. So I'll try to explain which domain I'm talking about here. But we're going to start with fast soft body simulation here. And I'd like to talk about a project that I worked on a couple of years ago and is still going. This is called ChainQueen. So ChainQueen is a fast, accurate, and differentiable simulator for soft bodies. Here you see a quadruped walker. It's walking forward with pneumatic chambers that are allowing it to gait. To perform a striding gait. And one thing I should say here is that this controller was not created by a human. This was automatically created by an optimization algorithm and done within just a few minutes. So let's talk a little bit about how this works. First, I'd like to say why we care about simulation. Like I said, every time you change the design of a robot computationally, you want to simulate it to see how well it's performing. So the faster that your simulation is, the faster that we can design different robots. Differentiability is the concept that any quantity in a simulation can be differentiated with respect to any property of the system. This includes differentiating, say, a loss function, like how far forward has my robot walked in a simulation, with respect to things like controller parameters or material parameters. And this is really important. This is how we're going to get really fast controllers. We're going to have gradients of how do we optimize, the forward progress of a robot with respect to the control parameters of a neural network that's working as closed loop control. And that's going to allow us for super fast optimization of controllers. And this is also going to be useful for co-optimization, which I talk about soon. A lot of times people ask me, why did we have to create a new simulator anyway? There are existing simulators out there. One of the, most of them have some level of differentiability or some level of ability to handle soft bodies, but there was really a small space of when we created this, and I think still true today, a small space of simulators where we have gradients, where it's fast, and that can handle soft bodies. So this was the state of the art in terms of speed, and it was the first one that was fully differentiable. And our simulator is based off something called the material point method. It's sort of similar to FEM, but it's a little bit different. So I'll talk about it briefly. It's extremely popular in computer graphics. So it can simulate multiphysics, like snow, water on elastic bodies. If you want, you can torture this poor bunny and squish it into 4 pieces. And it's pretty simple to implement. It's a pretty simple idea. The idea is that your robots or your characters are represented as arrays of particles, and each particle embeds something about the robot state. So it represents the position, the velocity, the strains of each point on the robot, and the collection of those particles sort of like atoms or molecules, make up the bulk of the robot. Now, the nice thing about material point method is that it can implicitly handle collisions between the robot itself, so inter-robot collisions, and the environment itself. And the way it does this is it has a background grid, which is a second representation it uses. And this implicitly handles collisions between different parts that are coming into contact on the grid. For the purposes of most of this talk, you only have to think about it as a particle collection, but the grid will come into usefulness later. The nice thing about using particles and grids as representations for soft bodies is that they're really good collections for parallelizing. So it's really easy to write or maybe not easy, but it's straightforward to write a GPU implementation where we have simulation of all these components in parallel on the GPU for the forward simulation. But we also can use the GPU in order to compute gradients of the system. This is what a robotic simulation looks like, I would say, especially for soft robots. You have some robot state, and then you have some observer function. The observer function takes the total state of the robot and observes it in some way. We'll talk more about this later, but I want to ground this as then that's fed into some sort of closed loop controller. It could also be an open loop controller if you want. That produces an actuation signal, and then we apply the material point method simulation step in order to forward simulate the robot. And you just repeat this over and over again. And if you want, you can add sub-stepping here into the simulation step. Now, if you think of what I just showed you as a single step in time of the robot, after you've simulated the whole system forward, you can compute a loss function. So let's say I simulate the soft robot walking forward for something like 4 seconds. I compute how far did it walk from its final location compared to its beginning location. And that gives me a final loss. And I want to try to maximize or minimize something about that property. We'll try to maximize how far forward the robot's walking. You can also deal with things like running losses. So how much actuation are you using at each time step? So you want to minimize the total energy cost of simulating the system. But the nice thing is that you can think of each one of those steps I showed you in the previous slide as a single block in time. And if we can compute the forward simulation of any one of those blocks, and if we can compute the gradients of that block of all the outputs compared to all the inputs, then we can simply apply a recursive application of the chain rule in order to differentiate the whole system of the entire simulation from the end of the simulation all the way back to the beginning. And that means that we can take the gradients of some property of the entire simulation, like how far forward did we go, with respect to the controller parameters and all the material parameters or shape parameters of the system. Really quick before I show some cool demos, why do we want a GPU implementation, which we have a gradient computation also? Well, you could just code it in TensorFlow if you wanted to. You could just code the simulation, but we're 132 times faster than the reference version. So it's pretty important to be able to make things fast for the inner loop. So that's why the GPU implementation is so important. TensorFlow will put things on the GPU as well, but it's not optimized for the task. And we were about 4 to 9 times faster than the state of the art. All right, let's get into some cool applications. First, it's a toy example. So you have some simulations where you want these balls to collide into each other and hit the blue location. And by just like 3 iterations of gradient descent, we can get there. And it can recover what are the relative densities of the system have to be in order to reach the target location. So this is just a little application of system identification, super simple. But we can do this now also. We have some results coming out where we can do this for any property of the system, stiffnesses, Poisson's ratios, densities, and so on. What's really more exciting is how can we use this simulator in order to do fast controller design. So we're just going to use the gradients here, and we're going to apply gradient descent. And what you're going to see is that as more iterations of simulation occur, the robot learns to walk forward. And this is just gradient descent using differentiable simulator and backpropagating to the controller parameters. This took 58 iterations, but we can do this much, much faster now. We can do this in like 10 iterations by using atom instead of just vanilla gradient descent. And we can simulate this extremely fast. So this problem can be solved in a matter of seconds for the 2D biped. I showed the quadruped runner. This is a slightly more realistic example because it's actually 3D. Right, and we see over time, again we can optimize this faster than 50 iterations these days. But these were the results a couple of years ago. Okay, we can do crawlers. I won't talk about this too much, but I just want to show that you can have different types of actuation patterns. And one of the questions I get a lot is, can we do geometries other than cuboids? And yes, so for the Pokemon fans out there, here's a Bulbasaur, and it's learning to hop forward. So you can just give it any STL mesh you want, tell it where the actuators are nowadays, and we can simulate it and we can optimize it to hop forward. One of the other questions I get is, why do we care about doing gradient-based optimization of soft robots? After all, we already have reinforcement learning, and reinforcement learning has been so good for rigid robots. Well, first of all, it converges faster in cases with no contact. So we had like an arm that wants to hit a target point. By using gradient-based optimization as opposed to reinforcement learning, we can converge 10 times faster. But also for a case with contact, in all of our experiments, we found that reinforcement learning is extremely slow for optimizing soft robots. The simulation is slow, and that's the bottleneck in reinforcement learning. So because you need so many simulations, because it's so hard to parallelize when you're using GPUs, we need to it's just going to be so computationally expensive. So reinforcement learning isn't very viable for walking soft robots. And so, we let this run for hours and it really doesn't converge well. But gradient-based optimization, we can do in a matter of seconds. So there's just really a stark difference. All right, so that's enough of just why do we need simulation. And now I want to talk about why do we care, how can we use differentiable simulators of different types in order to optimize the structure of robots at the same time that we optimize for the controllers of different robots. And one of the things that we should talk about really briefly is, why are co-optimization algorithms necessary? Why would you want to optimize for the structure and the controller of a robot at the same time? Well, here's a little cartoon example, not to scale. Imagine you have this short robot, it's 10 centimeters tall, and it wants to hit a button that's 15 centimeters off the ground. So it needs to walk forward and hit the button. This thing is too short. Unless it somehow jumps, it's going to be unable to hit the button. So the logical answer is that we need to make the robot taller. So we redesign the robot and we make it 15 centimeters tall. Great. Now our robot can walk forward. But in doing that, we have to change the controller as well, because the torques that are applied on the different parts of the body are going to be different. And also the kinematics of the system are going to be different. A short striding robot is going to be different from a long striding robot. And all these different components interplay with each other, right? As you change the controller, you're going to have to change the design. Or as you change the design, you're going to change the controller. As you change the controller, that's going to change which actuators you need. And different actuators take up different sizes. They have different bulk. So you're going to want to maybe redesign your chassis of your robot in order to hold the motor. Now you're back to having to change the design again, and this goes around in circles. So we would like a really simple way, a straightforward way of co-optimizing all these aspects instead of a cyclical design process. And our solution for doing this is based in trajectory optimization. So many of you are probably familiar with the idea of trajectory optimization. But the idea here is that you give a task, you give a target goal in the form of constraints, and trajectory optimization solves for what is the actuation sequence you would need in order to get a dynamic motion that can satisfy those constraints. So maybe you have a starting position, a target position that you want to hit, and you want to minimize, you want to find a motion that satisfies the starting and ending position, and you minimize some cost. What we showed in this work is that you can directly add parameters into trajectory optimization, and this can turn into co-optimization process. Right? So this, I just want to mention here that a lot of people wonder, can you handle contact here? For that hexapod, is there a way of, as you change the system, also making sure that the contacts with the ground are satisfied? And yes, this is a method that also handles robots that walk on the ground. So As input, you might have a robot like the hexapod that I showed you, parameterized in different ways. So what are its lengths of its different components? What are the masses of the different components? What are the inertias of the different components? And then you give it some sort of target task. So I want the robot to hit this red dot. Now, of course, the robot is too short to hit the red dot with the center of its nose. So the algorithm is going to have to automatically learn to change the parameters of the system in order to solve the task. We also minimize for the total actuation needed. And the reason, or I should say the maximum actuation needed of any actuator. And this allows us to down select the smallest actuators possible. And then not shown here, but we also have a constraint that makes sure that these actuators are fitting inside the design of the robot in a continuous way. The output will be the optimized parameters of the system and also the controls that allow the robot to walk forward. And lastly, it'll tell us which actuators we need in order to build this thing. So some results. So, you know, we can do a biped robot, and we can have the robot just walk forward in a way that is energy efficient. We also have the ability of the biped to jump upstairs, and this is all optimized for, you know, everything here is solved automatically. It automatically learns that it needs to have short upper components of the legs so that it can actually hop over the stairs. Because if you made the top ones long, it would be very difficult. Here's an energy efficient gate for a quadruped. And as we'll show, we can also do fast running. If we want to change the objective, that's fine. This is well, it was supposed to be a squirrel, but it really looks more like a scorpion. So this is the scorpion robot. It has a tail. This is really complicated because we want both the front of the robot to hit a certain target point, and we want the tail to hit a certain target point. Again, for all these examples, the robot was in a bad configuration where it wouldn't be able to solve the task before it changed the parameters. So we usually made the robots also too heavy to walk, and the algorithm has to automatically find good parameterizations. We can also build these robots. We built the hexapod, for instance. If people want, they can go check out the video. The biggest issue with going from sim to real with rigid robots, as people are probably aware, is dealing with friction. So the kinematics, the dynamics of the system match, but when it hits the ground, it just doesn't quite move as much. That was an example of how we can use co-optimization to design rigid robots to solve different tasks. I want to talk about moving to more compliant robots. And I want to also talk about how we can not only optimize over geometric and inertial parameters, but how we might also try to solve for our actuators. This is a very hard task in robotics of where do you place the actuators down? How do you design them? That's one of the more major parts of designing a robot. So here we're going to talk about cable-driven robots, and we're going to add some compliance. So we're going to put springs in the joints. So now we're sort of halfway between rigid and soft robots. So this is just a little cartoon. You can imagine there's in the middle there's a cable here, and as you pull on the cable, the system compresses. And the kinematics of how the system compresses depends on where you route the different cables and also the different torques that are in the springs. So this was some work I did at Disney. And let's say you have a character and you want to hit a certain pose. How do you route the cables in a way that allow you to achieve that pose? And how can you do it with as few cables as possible? So, you know, maybe you have to input some target poses. And then you have as candidates a large selection of different possible cables that you could use in order to actuate the system. This is tons of cables, like 4,000 cables, in order to hit those poses. We need an algorithm for down selecting what are the most relevant ones are in order to hit the poses as accurately as possible. And this is a co-optimization problem because we also want to solve for how do we pull on the different cables in order to hit the certain poses. I want to jump forward to just some more examples. Right, this is the fighter character you just saw, but we can also do things that are maybe a little bit more interesting for robotics. So we have this gripper. And this is a gripper that needs to be able to hit different poses for different shapes that it wants to grasp. And depending on the objects that we expect it to be able to grasp, we can optimize the motion and the task. So this might be interesting and useful for industrial robotics, where you're constantly trying to grasp similar shaped parts, and how can we optimize and simplify the design of that. We can also do different gestures with a humanoid hand. So again, we give it input poses that we want the hand to hit, and it outputs how we should route the cables in order to do that, and how we should pull on the cables. All right. One of the things here that you might notice is that cable selection is a complex problem because it's a discrete problem. So here we're mixing a discrete optimization of where do we put the cables with what are the actuation signals that we want to put in order to actually achieve the motions that we want, right? And this is a one-time trick that we can sort of use. The system is always in static equilibrium. We always want to hit certain target poses. And we sample a huge collection of possible different cables. What this allows us to do is we can pre-compute all the different motion arms of all the different cables with respect to the torques, the springs that they're going to, the joints that they're going to move. And that allows us to build this really dense H matrix. And in static equilibrium, you have an equation which is the moment arm times the force that's applied on the cable is going to be equal to the torque. So we can build up this really large linear system. And if you can match this linear system, if you can solve it, then you're in static equilibrium. So all these poses are in equilibrium. And then what we can do here is we can come up with the following dualism. We realize that a force that is 0 is the same thing as having no cable at all. So we can run a sparse minimization process, sort of like the lasso from statistics, and we can co-optimize over minimizing the number of forces that we need, the number of cables that we need, and also the forces themselves that we need to pull on the resulting cables with. So, and then we can actually post-process it and make the results even better. So that's just a high level. This works for this situation, but it doesn't work for all situations. And I'll talk more about complex structure in a bit. Okay, going back to fully soft robots, so there's also interesting co-optimization problems here. So one of the things that you care about is the materiality of the system. Where should I, if I'm making a soft robot, if I have the ability to say digitally manufacture it, where should I put rigid components? Where should I put soft components? Where should I make it compressible? Where should I make it incompressible? And so on and so forth. So here we use our ChainQueen simulator, and we're able to directly co-optimize over materials. That's the stiffness, the Poisson's ratio, and the density of the system at different points in order to optimize the forward gate. As you see here, you can sort of see that there's this pattern that sort of comes out. You see like these almost symmetrical places where places that we don't want the system to deform become stiffer, places that we want it to deform more become even softer, and places that we want to maintain a structure, say they tend to stay incompressible. And what results is sort of this resonant motion, this harmonic periodic gate, where the materiality is informing the gate. It's the best materiality possible for that cyclical motion. So the structure encodes the type of motion that we want to get. So the actuators are no longer working against the motion, but rather with the motion. And we can do this for all sorts of walkers. Okay, that sounds good, but does it actually work? And the answer is resoundingly yes. For each new component that we add into the co-optimization, everything above control, so we add in stiffnesses, or we add in Poisson's ratio, or we add in densities, everything extra thing that we can co-optimize over helps to improve the performance of the system. I think the Young's modulus was most important, followed by density, followed by Poisson ratio. But we can get up to like a 40% increase in the forward gait, the forward distance that the robot is able to walk by co-optimizing over all these different parameters. So this is really, really valuable. If we can achieve this in real life, we'll be able to really improve the performance of our soft robots in a meaningful way. Okay, but sometimes co-optimization is not enough. Sometimes we need to be a little bit more intelligent about how we're going to design our systems, especially in the case where we have complex discrete structure. So this is where we turn to machine learning algorithms to try to make our searches more intelligent. So you might be asking why learning-based approaches? Well, one is because the complex nature of robots, but also because co-optimization, direct numerical optimization schemes, they tend to get stuck in local minima. So we need new algorithms for this. So again, I'm going to start with rigid robots, and I'll work my way back to soft robots here. So let's just start with a little thought experiment. You have a collection of links, maybe like a Lego set of links that you're holding. You have a bunch of joints, so you have these all in a bin, and then you can snap them together, right? You can snap the links to the joints in different ways. What is the space of robots that we could build? It turns out you can build a lot of robots. That shouldn't be surprising. The space of kinematic trees is enormous. But it's really hard to navigate that large space of components. And so one of the ideas we had was, could we create a grammar that allows you to search over the space? So we created a language where you perform substitution rules, and by applying these substitution rules, it produces the output structure of a kinematic robot or dynamic robot, but in the form of a kinematic tree. Now, the reason why you want to use a grammar here as opposed to just allowing people to connect anything to anything is because it can sort of steer the search in intelligent directions. You can maybe encode that you care about leg pairs, or you care about robots having interesting tail structures. This doesn't constrain the space in ways that doesn't allow, you can still create any robot you want with this grammar, but it does sort of force the search to look around for structure that is encoded in the grammar. So this is basically just rule-based composition. You have a starting node, you create a head, a body, and a tail, and then you apply another substitution rule where you expand out the body, so you make it a longer body. And then the body can be replaced with leg pairs, which have an encoded structure. And then maybe the leg pairs, you decide you want to make them double links, so you make the legs longer by doing another rule substitutions. And then you're done, right? And you can replace, you have all terminal symbols, you have all actual components that you can build. So in doing this, we had intermediate designs. This is not something you can fabricate because we don't have a component for what the body is. But by the time we get to the end, we can substitute in all the intermediate components with actual components from our toolkit and make it a physical object. Okay, that's cool. Restricting this design space, or not restricting it, but guiding the design space helps. But the space is still exponentially large, right? So we need a search algorithm that's more intelligent to search over different structures of these rigid robots. And we're inspired by A-star search. So imagine you want to apply different substitution rules to build your robot. How would you actually go about doing this? Well, imagine you have a heuristic function which optimistically tells you how good the robot will be if you take different rules. Well, then we greedily just follow this heuristic function, and we go down the path that's going to give us the best gain. We get a robot at the end, and then we can simulate it for something like how far forward can it run, or how energy efficient it is. Maybe it runs forward 2.5 meters after we actually simulated it. So this heuristic function thought it would have a value of 2.6, but it was 2.5. Heuristic function was pretty close. It was good at guiding the search. I haven't talked about how that heuristic function comes yet. I'll talk about that in a second. And so optimistically, we see that even partial designs, we can say, based on our experience, how good they're going to be. We add some exploration to this. We take an idea from reinforcement learning, we do epsilon greedy search, and we go down a different path next time. We try to optimize a different robot. And we result at another robot, and we simulate it. It works pretty well. And so then we have an optimistic estimate of how good these different partial designs work. And we can keep repeating this. And eventually the hope is that by applying this epsilon greedy strategy, we'll intelligently search the space in a way that we find the best robot. But one of the problems here is I haven't told you how you got this heuristic function, sorry. And the way that we're going to do that is we're going to use this data that we generated from the simulation. And every once in a while, we're going to take the data that we've generated, and we are going to learn a heuristic function as a graph neural network. So the nice thing about rigid robots is that they have a topology encoded in them, and it maps really well to a graph. So from any one of these robots, we can extract a graph in the form of the nodes are the links of the robot, and they encode, you have feature vectors there, which are certain properties, and the joints will encode the topology of the structure. So we take what we learned. We have a mapping of how good a design is to how good the design structure itself, to how good the design performed, and we can use this to iteratively improve an estimate. And so we just go back and forth of sampling robots and learning this heuristic function. And we can do this not only for one objective, but we can actually also extend this to a multi-objective scenario. So we can optimize for multiple objectives at once by searching for and keeping track of Pareto fronts of designs. So I'm going to show you, this is recent work we just submitted to ICRA, where we are optimizing for different design trade-offs. So I'm just going to show you some cool results really quickly. So let's move on to, this is a problem where you have a robot that you wanted to, for instance, be able to traverse a walled terrain, or you want it to be able to jump, and you want to create robots that have different interesting trade-offs of these two objectives. So some robots will be able to jump and to be able to walk forward. Other ones will just be really good jumpers, and other ones will be just really good walking robots. So I should trim this video a little bit, but yeah, so here's some examples of some optimized robots for jumping. So this is an example where the system automatically optimized for both the design and the controller simultaneously. These are robots that can walk, that can jump, but also ones that can move side to side and navigate this terrain at the bottom. And lastly, here's a robot that can walk really well, but see at the very top, it's very bad at jumping. We can also do trade-offs of different sort of power configurations. So you might have strong motors or weak motors, and having weak motors, this might be an example of a case where you're running low on battery, so you can only use your motors at certain percentages. As the system becomes more aggressive in the normal motor case, where you have full power, you'll see that the legs get wider and wider is the optimal design. So it can maintain its, it can lift itself off the ground. But at the top, if you're only in the weak motor configuration, the robot's just going to flop forward. So this is some interesting trade-offs of how you can optimize for different robots for those two tasks. I'm going to skip forward a little bit. This is a 3-robot example. A 3-objective example. The results are pretty interesting, but I think what's most interesting is what we got out of a place where we want to optimize a robot to spin in place. You can see here's one example of a robot that does all 3. It spins, walks, and jumps. But here's on the left-hand side, we have, this came right out of the optimization. We have a figure skater robot on the left and sort of this breakdancing robot on the right. So that was really cool because the system automatically designed that robot and optimized its controller to be able to do those tasks. Going back to soft robotics, there's a question of can machine learning help to design soft robots that are capable? So if you recall, I showed you this figure earlier, and one thing I skipped over is this observer function. Whenever you're dealing with soft robots, they're infinite dimensional creatures. So we need some way to reduce this high dimensional state down to a low dimensional state that can be fed into a controller. If you try to feed the entire state, even if you approximate an infinite dimensional system as like tens of thousands of dimensions, it's very hard to actually learn. It's very slow, and sometimes it gets stuck in really bad local minima. Right. The way we did this in ChainQueen then is we manually created an observer function where we clustered different parts of the robots together, and we computed their center of position, the center of velocity of each one, and we fed this into a controller and we learned it over time. This requires some human tweaking, and you can't actually measure in real life where every particle is on a system. So we have this idea that maybe we can learn to control these soft robots from vision. So we have an optimization scheme, which we call learning in the loop optimization, where we interleave learning the structure of the robots, the structure of the observer with optimizing the robot's controller and materials. And the way we do this is we alternate learning and autoencoder. And this is really nice and easy because material point method occurs on a grid. So we can use the convolutional neural network to learn from the grid states, those intermediate grid states I talked about, of the data that we generate in simulation. So during simulation, we generate lots of data of different grid states. This is actually and the data that's in these grid states is the velocity of the robot, both in X and Y at every one of these pixels. That's actually something that's physically measurable, because that's something that you can get from optical flow, from dense optical flow. You can approximate how fast different parts on your robot are moving. And so we can pretend we have a camera model here, and we can learn from the different data that we generate in simulation, learn observers over time, and then use the learned observer to optimize the control and the material distribution of a soft robot. And that's exactly what we do in this paper. And what we find is that the system is able to learn much better using this type of an observer, a learned observer, than using any of the ad hoc methods that we did, including things like clustering. So not only is this something that's possibly physically measurable in the future, but it's also something that has better, the observer function is properly catered to the types of motions that it expects to see. And the latent distributions, those compressed vectors that we get out of the autoencoder, they're actually semantically meaningful. So you can see subspaces of different types of motions emerge over the training process. One last thing I want to talk about of ways we can do learning, this is something we submitted to RoboSoft this year, is maybe what you want to do is you actually want to learn not a camera model, but strain sensors. Where do we put strain sensors on our robots in order to optimize them for solving certain tasks? This is very important. If you want untethered soft robots to go into the world, we want them to work purely with proprioceptive features. And so we presented this this work recently. We submitted to RoboSoft, where we have an adaptive method that, at the same time that it learns to solve certain tasks, it's going to learn different distributions of where should we put the sensors on this robot, where should we put the strain sensors, in order to solve these tasks as best as possible. And what this comes down to is a really strategic learning architecture. So we use a point net-based learning architecture that learns over time how to solve certain tasks from the strain inputs, and each point in the system has strain information, and these are sort of the RGB channels of your point net system. And then what we do is we say the front layer, the input layer of this network, is actually going to be a sparsifying layer. So we can go in, so the system over time will learn to drop out selectively, based on a probability distribution, which sensors are least interesting for solving the task. And we can knock it down from a collection of 400 strain sensors to something like 5 or 10 or 15 strain sensors in order to solve interesting tasks. So these tasks would include things like, if you want to disambiguate which shape I'm grasping. So this is from time series data. How do I know if I'm grasping a circle, a square, a triangle, or so on? Or we can try to disambiguate the stiffnesses of the different objects that we're grasping. One thing I don't have time to show here, but we can also do proprioception. So just from strain sensors, we can reconstruct the deformations and the deformation rates of any point on the soft body. This is just to show that we do much better than baselines, which have trouble of even learning anything. So we're actually able to, these sort of fail, but we can learn good distributions of sensor locations with our method that are able to converge to really good results. But we can also use this for control. So we can learn, we can learn where do we put control sensors on the system in order to be able to control the robot walking forward. And if you see here, each of these little blue circles on the robot is a different sensor. And again, this learns a latent space that's cyclical. So the controllers that we learned here are meaningful, and they're using the strain sensor to create cyclical controllers that make sense. Okay, I am extremely low on time, so I just want to quickly talk about some work we're working on in fabrication and user interfaces. We have the ability to, one thing we worked on recently is trying to fabricate these sensor arrays. So we came up with this project where we work on making a soft glove that can reconstruct, at least now for hands of people, but hopefully over time they'll be able to reconstruct the structure of robots. And we can get state-of-the-art hand reconstruction using this architecture. Really quickly, the way that it works is that it has both resistive and pressure-based sensing, and we can use the dense arrays of resistances that we measure from a fully conductive glove, which is knit, in order to get the in-hand pose reconstruction. We also have pressure-based sensors on the front of the glove in order to measure interactions with the world. It's really simple to make. It's purely fiber-based. It costs like $60, and it's all from learning. So we're hoping to use this structure to optimize sort of robot skins. We can do lots of things with it right now just for human wearables. We can get accurate joint reconstruction. We can measure temperature. We can measure grasping force, handwriting accuracy to 90%, heart rate of the wearer. So it's a really cool sensing architecture, and we're really excited about how it can be used to make robot skins. And I'm basically out of time, but hopefully the vision here is that in the future, we have these full CAD CAM workflows where you have simulation in the loop, you have the ability for a user to interact, you have the ability to automatically output designs for fabrication, and the system helps guide users in terms of optimizing the different designs according to certain tasks that we want. And hopefully, one day we'll be able to output these directly to digital fabrication devices, such as 3D printers. And we'll be able to create large suites of robots. These are obviously toys, but right now we're working on trying to make much more dynamic robots like the RoboGrammer robots you saw before. And ideally also, because it's a stack, hopefully we'll be able to swap out different components. So if we decide we want to make metal robots that are water jet as opposed to 3D printed robots, hopefully going back to the stack idea, we'll be able to swap out any layer that we want and be able to improve, and be able to use all the capabilities below in an intelligent fashion. Just philosophically, I'm really excited about computational robot design. I think it's going to be, it has the potential to be a force multiplier for the field, because it'll not only accelerate the workflows that we have for design and fabrication, but it'll do so in a way that allows us to explore lots of different robots. So it's going to speed things up, and it's going to, for the robots we're already creating, and it's also going to allow us to explore things that we never thought we'd be able to explore before. There's a ton of future work before this really becomes practical. I think that what we all should be looking forward to in the future is that, I showed you a lot of my work that works mostly in simulation, some stuff we fabricated. A lot of work right now coming out of different groups is just, running Majoko, optimizing some rigid robots and calling it a day. But, once you get to fabrication, you may find out that your model didn't work. So the future of the field really needs to start moving, I think, towards treating fabrication as a first-class citizen, and I'm guilty of this as well. There's going to be a really hard time bridging the sim to real gap, especially in cases where you have contact. So this is going to be a really interesting space for fabrication and how simulation parts of the stack interact with the fabrication part of the stack. I showed you some examples of co-designing over actuators, materials, shapes, sensor placement. And I think a really interesting question, and I think Andrea, for instance, has really interesting work going on in this space, is how do we make a unified theory of how all these different components can work together? How can we co-design all different aspects of robots? We want, we in the same way that we have a computational stack has modularity, I'm hoping that the tools that all researchers and developers are creating around the world, we think of good APIs in which these different sorts of components can interface with each other in a way that they can be plug and play. And lastly, right now, all these tools, these robot design tools are mostly, they're not integrated into any CAD workflows. They're mostly just things that researchers work on. So we need to start thinking about how can we start making these tools, as they become more mature, available to robot designers around the world. So that's the end of my talk. I welcome any questions. I know I'm running very low on time, but thank you so much for listening, and I'm happy to talk about anything anybody wants to ask about.
Thank you very much, Andrew. Very cool talk. Are there any questions from the audience?
I kind of need to absorb, the whole concept.
Maybe I should make this talk a little slower next time I give it.
Yeah, no, well, no, there is a lot, right? So there is a lot that you are trying to say and convey. And clearly, there is a lot of work, behind all of this. Now, so my first reaction was that what you were showing were some kind of like robots that are essentially like a giant amoebas, right? But well, as we know, as we observe, like nature has evolved from that, right, and introduced things that are more like some specialization, right? So there are some cells that are good at doing certain things that other cells are doing.
Yeah, there's biodiversity.
Other things. Even within, like a single cell organisms, right? So you have some organs, and so you can have, propulsion devices, and you have energy production things, right? Things like that, like. I see that you introduced that by you had these kind of like actuators, right, and joints and things like that. But then you what you have is this like a big explosion of you search on this graph, right? So I just trying to understand how all these things fit together. So it's not that
I think there's still a lot of formalization that has to go there into how different tools and different robots are going to work in different domains. In the same way that we sort of have different kingdoms of life, we sort of in some way had different kingdoms of robots. We have rigid robots, we have soft robots, we have hybrid robots, and for each of these types of robots, we need different capabilities. Certain types need good proprioceptive sensing. Certain types need an interesting skeleton. Certain types are more blob-like, like amoeba-like. And I think that going forward, we need to understand which of these optimization methods are actually general, which can just be used to search for any types of components, and which are kingdom or domain specific. Certain optimization algorithms are only going to work for certain types of tasks. So like discrete selection versus continuous selection.
You may also think that, is it right to fixate so much on optimizing a task?
That's a great question. I think the answer to that is both yes and no. I think the answer is yes, we should be focused deeply on optimizing robots. But I think that the answer is no, we shouldn't be optimizing them for a task. We as humans or any other animal do tons of things. We run, we jump, as humans, we write, we walk, we can drive cars, we can ride bicycles, we have so many skills, and we can learn different skills.
Right, but in a sense, when you're thinking of, so it's not that we are trying to create a species that will be successful and colonize the universe, right? So, when we make a robot, well, until unless we get some ambitions, right? But let's say that we still think of robot as a tool, right? So then maybe as a tool, you really want to build a tool that performs something specifically, right?
I mean, yes, but at the same time, most of the things that you want to do, for instance, requires more than just one skill. So like if you wanted a cooking robot's going to have to be able to grab tools. It's going to be able to have to do like dexterous manipulation. It's going to have to be able to chop up vegetables, maybe. It's going to have to be able to learn to plate things. Just cooking alone has tons and tons of different skills. So there's definitely like we need to be able to make robots that can be skillful in a number of different subtasks in order to solve larger goals. I think that there's probably, in the same way I showed the multi-objective optimization of the rigid robots, I think that we're probably moving in a direction where we want robots not only to be able to do 2 or 3 tasks, but maybe like 20 tasks, or even in a continuum of tasks. But I think it's an open debate of whether or not we want robots to be able to work for, do we just want you buy Cookbot and you put it in a kitchen, or do we want robots which are more similar to humans, which can be masters of all trades? I think that that's a very hard question, and it will also be interesting if we can optimize robots to be masters of all trades, or the ability to learn all different traits, will the structure match what biology has found at the end of the day? You know, is a human optimal for these sorts of tasks? Probably, because we created our environment actually modeled after the human. But, you know.
Yeah.
I have a question / comment.
Sure.
So I really like everything, but the first part, I think that what's very interesting is this new kind of representation for you know, modeling the robot body, and you know, I don't know that the theories, I need to look at it, but this mixed you know, cells, particles, and so on. And I also like that you could the idea of differentiability to a simulation. And I was just kind of thinking, you know, what are the limitations of this? Because I think at some point you said, you know, this is all differentiable, and there, you know, maybe okay, but then you said something like they say, no, but we need machine learning because I suppose things are not convex. So my question is, can you clarify a little bit the, you know, what are the limitations? And the other comment that I had is that, you know, the way you presented it, you know, the soft robots and the rigid robots are kind of two separate domains with, you know, different parameterizations. And I'm wondering, okay, can you do, what would be the union, you know? Can you have joints and then, you know, you have soft mass attached to the joints? Because I think here, you know, the way evolution goes, right, it's that for vertebrates, you have, you know, bones or kind of equivalent, and then you have like soft mass around it.
Yeah, absolutely. Okay, so I'll take the second question first, because I think the answer to that is a little bit more straightforward. Yes, there is definitely an extremely interesting space where you have skeletons, then you have soft components sort of grafted onto the skeletons. That is an extremely important space also. And lastly, it is an extremely difficult space. I spent a large amount of time in the middle of my PhD trying to do stuff in terms of modeling this. And it's hard to model rigid and soft components simultaneously because rigid and soft components work on different energy scales. They have different types of forces. And you know, one's a finite dimensional system, one's an infinite dimensional system. So I'm not saying it's not possible, and I'm sure somebody will crack it in the next few years and have this awesome paper where they show how you can model these well and you can optimize them well. It's just harder to do than purely rigid or purely soft together. But it's important, like you said, and like I mentioned at the beginning of my when I was talking about the different organ systems, right? And like you mentioned, we have skeletons with soft components around them, and that's what allows us to have you know, easy articulability, but also the ability to manipulate and easily grasp with compliance. The other question about where do you need optimization versus learning, that's a, you know, a fuzzier answer. I think that a lot, you know, there's a lot you can do in terms of, it depends on first of all, it depends on what type of optimization process you want to use, right? There are discrete optimizers, there are continuous optimizers. Differentiability and continuous numerical optimization can get you a decent ways with modern neural network controllers, with the right types of dynamics of your system. But for instance, I tried making a really tall, soft robot that fell over and over again when I tried to optimize it, because it's forward. The optimization process said, go forward as fast as you can or as far as you can. And the best way to do that was for the robot to just keep falling forward, right? That was a really great way for the robot to make forward progress. And I tried to craft this objective function like 10 million ways to get the robot to just sort of walk forward. And it was so difficult to do. This was a case where I had like a soft robot with basically pneumatic knees in it. It was a disaster. So the problem of constantly getting caught in local minima suggests that you need, it doesn't have to be a learning-based approach, I don't think, although I think that they are particularly effective, but you need some sort of discontinuous search that is surrounded around your continuous search, because otherwise you'll get stuck in these local minima and you'll be unable to solve these tasks. I think also learning or search-based approaches are necessary if you have if you want to solve really complex structural problems, unless you're very, very clever about the way you formulate your optimization problem. It's possible that everything I talked about could be like formulated as a single optimization problem, but I don't know the way to do it.
Mm-hmm.
Did that answer your questions?
Yeah, thank you.
Are there any other questions?
I have a question.
Sure.
Go ahead.
If we have time. Quick one, I guess. First, thanks for the awesome talk. My question is about, I guess, robustness and tuning. So, yeah, I guess how much tuning effort is involved in producing some of the results, and
yeah. Okay, so once you've sort of cracked any of these algorithms, for the most part, there's not a whole lot of tuning that had to go into any of these. Finding a good recipe that works on that's pretty general. You know, all of these problems have some hyperparameters, but I don't think any of them, at least the ones I showed today, have a ridiculous number of hyperparameters or a ridiculous number of amount of tuning. I think, for instance, for the grammar search of robots, we have a stable set of parameters right now that doesn't require any changing. The main thing there was just playing around with things like the learning rate of the optimization and the batch size for learning. And this is something that you can search over pretty quickly. For the optimization of the soft walkers, just learning rate is really all that I play around with there. Everything else I use mostly the same components every time, just a 2-layer neural network, and I tweak around with what are the ranges of the physical parameters a little bit. When you get to the trying to fabricate these things, you'll be locked into the physical parameters of your world anyway. Other things like the glove example, I think we played around with a few different architectures, but the short answer is that for all of these, eventually we came around to a single architecture or a single algorithm or a single optimization structure that probably has no more than 1 or 2 parameters that you might want to tweak at runtime. So I'm very bad at tweaking parameters of systems. So I tend to steer away from methods that require too much tweaking. It's too much black magic.
okay, thanks.
Any final question? If not, you have here the email, Andrew's email. I'm sure if you have more questions, you can reach out to him. Andrew, thank you very much for the talk. It was really, really interesting.
Thanks so much for having me.
I will follow up maybe with some detailed questions or discussion thoughts.
Sounds great. Yeah, and anybody can feel free to reach out. I'm happy to take conversations offline.
Thank you very much.
Thank you.
Thank you. See you all guys next week. Bye-bye.